Chapter 20 ROC Curve and AUC Score. Next, let's see ROC Curve and AUC Score. These are important tools for evaluating the performance of a classification model, especially for binary classification tasks. ROC curve, Receiver Operating Characteristic Curve, is a graphical representation of a classification model's performance across possible classification thresholds. ROC curve plots two parameters, true positive rate and false positive rate. As you know, true positive rate equals recall, also called sensitivity. The x-axis of our ROC curve represents true positive rate, and the y-axis represents false positive rate. ROC curve is the sky blue curve in this figure. By definition, an ROC curve is a graphical representation of a classification model's performance across possible classification thresholds. But what does possible classification thresholds mean? Usually, we set the classification threshold to 0.5. That is, if the classification model predicts that a given data point has a greater than 50% probability of being positive, then the model classifies that data point as positive. We can, however, set the classification threshold to various values. A higher threshold makes the classification model less likely to classify a data point as positive. Conversely, a lower threshold makes the model more likely to classify a data point as positive. Let's recap true positive rate and false positive rate. True positive rate is the ratio of true positives to the sum of true positives and false negatives, which represent the proportion of actual positives that were correctly identified by the model. False positive rate is the ratio of false positives to the sum of false positives and true negatives, which represent the proportion of actual negatives that were incorrectly identified as positives. The true positive rate reflects the model's effectiveness for the positive class, while the false positive rate measures the model's error rates for the positive class. Therefore, a model with high true positive rate and low false positive rate is desirable. However, it is difficult to achieve both high TPR and low FBR. Why? If the model loosens the criteria for classifying a data point as positive, false negatives will decrease, and thus TPR will be higher. However, false positives will increase, and therefore the FPR will be higher. Conversely, if the model tightens the criteria for classifying a data point as positive, false positives would decrease, and thus FPR would increase. However, TPR would be lower because false negatives would increase. Let's look at this with specific values. Suppose we have 10 data points, with red being positive and blue being negative. The higher the data point is in the diagram, the higher the probability that the classification model predicts the data point as positive. These values are the probability that each data point is positive, computed by the classification model for each data point. The top two data points are those for which the model calculated the 100% probability of being positive. These are actually both positive. Below that are two data points, one positive and the other negative, which are calculated to have an 80% probability of being positive. Similarly, there are sets of two data points, each calculated to have a 60%, 40%, and 20% probability of being positive. Given this data and classification model, let us set the various thresholds that serve as the boundary between positive and negative classes. First, the threshold is set to 50%. Here, 6 data points are classified as positive and 4 as negative. Of the 5 actually positives depicted by the red dots, 4 are classified as positive. Therefore, the TPR is 0.8. Also, with the threshold setting, the model classified 6 data points as positive. However, 2 of these are actually negative. In other words, they are false positives. Thus, since 2 of the 5 actual negative data points are false positive, the FPR is 0.4. Now, let's increase the classification threshold to 0.7. With the threshold raised, the number of data points classified as positive was decreased to 4. It also increased the number of data points that are actually positive but are classified as negative, that is, false negative. So, the TPR dropped to 0.6. On the other hand, because the threshold for being classified as positive has been raised, fewer actual negatives were classified as positives. In other words, the number of false positives decreased. So, the FPR decreased. In other words, while the TPR worsened, the FPR improved as a result of the heightened threshold. Let us now lower the threshold to 0.3 and compare it to the case where the threshold was 0.5. By lowering the threshold, more data points are now classified as positive. So the number of actual positives that are classified as negative has been eliminated, and thus the TPR has increased. On the other hand, the decrease in threshold has increased the number of actual negatives that are classified as positive. That is, false positives increased, thus FPR increased. To put it another way, lowering the threshold improved the TPR while worsening the FPR. Thus, when the classification threshold is changed, if one of TPR and FPR improves, the other tends to worsen. We can compute TPR and FPR for various threshold values. This table shows pairs of TPR and FPR for various thresholds, computed using the data on the previous slide. Let's plot these pairs as points in this two-dimensional space. Then, by connecting these points, we can draw a curve in this way. This curve is the ROC curve, a graphical representation of a classification model's performance. The upper left of the two-dimensional plot represents a state of high TPR and low FPR. In other words, a pair of TPR and FPR in the upper left region represents high predictive performance of the classification model. Therefore, the closer the ROC curve is to the upper left of the two-dimensional plot, the higher the performance of the classification model. Thus, if we have an alternative model with this orange ROC curve, it should be regarded that the alternative model performs better than the original model. The 45-degree line drawn from the origin to the point 11 of the graph in an upward right direction represents the ROC curve of a model that randomly predicts positives and negatives. A random prediction is a prediction without any information for the prediction. That is, a model that predicts a case as positive with the same probability regardless of whether the case is actually positive or negative. Since an effective classification model must be better than a random prediction, its ROC curve should be above the 45-degree line to the left. Now, let me explain why the 45-degree line represents a random prediction. As mentioned earlier, in a random prediction, the model classifies all samples as positive or negative with equal probability. For example, a model that randomly predicts 50% of samples as positive will predict 50% of samples as positive, regardless of whether those samples are actually positive or negative. And a model that randomly predicts 40% of samples as positive will predict 40% of samples as positive, regardless of whether the sample is actually positive or negative. Let's consider using a confusion matrix. Let P be the probability that a random prediction model produces a positive decision. In a binary classification, a model's output should be binary, positive or negative. Thus, the probability that the model produces a negative decision is 1 minus P. Let X be the number of actual positives and Y the number of actual negatives. Since the model predicts a sample to be positive randomly with probability P, the number of samples classified as positive among the actual positives is Px. And the number of samples classified as negative among the actual positives can be expressed as 1 minus Px. Similarly, the number of samples classified as positive among actual negatives is Py. And the number of samples classified as negative is 1 minus Py. Based on this information, we can compute the true positive rate, which is P. Similarly, we can compute the false positive rate, which is also P. That is, TPR and FPR are equal in a random prediction. Also, their values are P, meaning that the TPR and FPR are equal to the probability of making a positive decision in a random prediction. It also means that the higher the probability that a random prediction model produces a positive decision, the higher the TPR and FPR will also be. In summary, in random prediction, TPR and FPR are equal, regardless of the cutoff value, although the values of TPR and FPR vary depending on the cutoff value. Therefore, the ROC curve for a random prediction can be drawn as a 45-degree line. As a quantitative performance measure, the AUC score tells us how well the model distinguishes between positive and negative classes. AUC is an abbreviation of area under the curve. AUC score can be computed as the entire two-dimensional area underneath the ROC curve. The ROC curve is drawn in an area that ranges from the origin to a point where both the x and y coordinates are 1, so the maximum AUC score is 1. The minimum value of the AUC score is 0 because the AUC score is an area and therefore cannot be negative. The higher the AUC, the better the model is at distinguishing between positives and negatives. The closer the ROC curve is to the upper left of the two-dimensional plot, the higher the AUC score is. If AUC equals 1, the model perfectly distinguishes positives and negatives. If the ROC curve exactly overlaps the 45-degree line, the ROC bisects the area and the AUC score is 0.5. Thus, when the AUC score is 0.5, it means that the model's predictions are no better than random guessing. If AUC score is larger than 0.5 but lower than 1, the model is not perfect, but the model's predictions are better than random guessing. If AUC score is lower than 0.5, it means the model is worse than random guessing. So, the model may have certain problems. Imagine a medical test to diagnose a disease. The ROC curve will show the trade-off between correctly identifying sick patients and falsely alarming healthy ones at various thresholds. In this case, correct identification is true positive and false alarm is false positive. A high AUC would mean that the test is generally good at distinguishing between sick and healthy patients. In summary, the ROC curve and AUC score are powerful evaluation tools for a binary classification model. The ROC curve helps visualize the trade-offs between true positive and false positive rates, while the AUC score offers a single aggregate measure of the model's overall performance. They provide insights into the model's ability to distinguish between classes. Besides, they are useful for imbalanced dataset because they consider both TPR and FPR, and therefore are less sensitive to class imbalance.